Welcome back. Dr. Mitt here. I wanted to prepare a short video that would help you to review our solar system diagram. I've already written that on the board, and this is just going to be a thumbnail, sort of an approach to what we've covered in classes. We've studied the planets, as we've studied some of the smaller celestial objects in our solar system. We'll begin, as is our custom, with an elliptical orbit. You'll remember that all of the planets, as well as asteroids and periodic comets, have orbits that are elliptical. We'll go ahead and do a circle here that will be the sun. Excuse me. And I'll go ahead and label the points of the orbit that are closest to the sun and farthest from the sun. The point that's closest to the sun is the perihelion. The point that's farthest from the sun is the aphelion. We also want to go ahead and put the line through the middle of here that, of course, we will label as the ecliptic. You'll recall that the ecliptic is the sun's pathway through the stars. It's also the plane in or near which all of the planets will remain because they're gravitationally locked to our star, the sun. So the ecliptic is here, and once we have the ecliptic labeled, then we can go ahead and put initials for the planets: Mercury, Venus, Earth, Mars. We're going to leave a gap for a reason, and then go out to Jupiter, Saturn, Uranus, and Neptune. As we think about the planets, we can think about ways that planets are classified. One way is on the basis of position. The other way is on the basis of size and composition. So on the basis of position, that's relative to Earth. And so these two planets, Mercury and Venus, are sometimes referred to as inferior planets. This is merely a term not to value the planets as if some planets are good and some planets are bad. This is merely saying that these planets are sunward. They're sunward from Earth to the observer on Earth. The planets from Mars all the way out to Neptune are referred to as superior. It's not that they're better, it's just they are spaceward from Earth. They're farther away from Earth than these planets, the inferior planets. Now, as we think about these, we know that the inferior planets also can make a transit. You'll recall that a transit just means that these inferior planets pass between Sun and Earth. They're not large enough, they're not of the size, the dimensions to be able to block the solar disk as we have in an eclipse. But these are just merely, it's just a thing that these inferior planets can do. They can pass between Sun and Earth. The superior planets can show what's known as apparent retrograde motion. Apparent retrograde motion. They can appear to change direction and to be going the opposite direction in their orbit. So we can be observing from Earth. It can appear that the planets are going one direction, and then it seems like they're going the opposite direction. That's called retrograde motion. The other way that we can classify the planets, again, is on the basis of size and composition. These first four planets, Mercury, Venus, Earth, and Mars, are what are known as terrestrial or rocky planets. And these other four planets are known as the Jovian or gas giants. The Jovian planets or gas giants. Terrestrial planets are Earth-like planets. The Jovian planets are Jupiter-like planets. These are also rocky. These are gaseous. We've left this gap in here. We're going to get to that in just a moment. But before we go too far, since we're kind of starting at the sun and working this way, you'll recall that we talked about a measure of the brightness of planets being done in terms of albedo. The albedo of Venus is 0.76. That means it reflects 76% of the light that strikes its surface. Of course, we know that that's because of its very dense atmosphere, but there are three factors that affect the brightness of planets. So we'll say brightness factors. As soon as we draw albedo for Venus, that reminds us that we have these brightness factors. There are three things. One is the distance of that planet from the sun. One is the size of that planet. And finally, the reflectivity of the planet's surface or atmosphere. So we have these things that affect the brightness of the planet. The distance from the sun, the size of the planet, and the reflectivity of the planet's surface or atmosphere. As we keep moving outward, of course, we encounter this gap. We're going to go ahead and kind of do a line up through here and label this as the asteroid belt. And you'll recall that we talked about this gap being the very reason that the asteroids began to be discovered. Astronomers in the late 1700s were looking out into space and they saw sort of a regular spacing of the planets or of their orbits. And they saw this extra space, what appeared to be an extra space between Mars and Jupiter. So they trained their telescopes on that part of the sky, and it was in the early 1800s that they started to discover asteroids. These have been called a number of different things. They've been called minor planets. The most current nomenclature that's used for the asteroids is to refer to them either as dwarf planets or as small solar system bodies. Of course, a few of the larger ones are called dwarf planets. Many of the others are small solar system bodies. We generally will call them asteroids. You'll also remember that we talked specifically about the largest asteroid being one Ceres, and the brightest being 4 Vesta. So the largest is 1 Ceres, the brightest is 4 Vesta. These were amongst the earliest. Again, the number is the sequence in which the asteroids were identified, that their orbits were understood and that they were identified and named. So they were given a number, again, the sequence of how they were discovered, or the sequence in which they were discovered, and the name, in this case, Ceres, in this other case, Vesta. So as we think about the diagram, we also remember again that an elliptical orbit could be something that a comet has, a periodic comet. And so we'll actually add to our diagram here with our comet diagram so that we can be reminded of kind of the structure of comets. They have 2 major parts, the head and tail of the comet. And then the head can be broken into 2 parts, the inner part that's the nucleus and the outer part that is the coma. The coma is the really bright part of the comet. It's what starts to melt. The ices in the coma are what reflect a lot of light, start to melt when it draws near to the sun, and it then produces the tail. We can also remember that it will only be close to the sun that a tail will develop, or even that a comet would even be visible. Out in space, way out here, the comets would not even be something that we'd be able to notice very much. But as they get closer to the sun, they start to produce a tail. And you'll remember that the tail of a comet is always at right angles sort of to the surface of the sun in that area. And the tail is always going to be blowing off into space because it's the solar wind and solar radiation that's causing the coma to melt, to deteriorate. And so the tail of the comet is always pointing away from the sun. Again, out in space, it won't be very obvious and there won't be a tail because it's so far away from the sun and its radiation. Not all comets have elliptical orbits. There are some that have what's known as a parabolic orbit, and this starts to get a little bit crowded here, but we are drawing a parabolic orbit. And the comets that have a parabolic orbit are not periodic comets. This is what I sometimes refer to as the one and done. They pass through or pass by the sun only once and then go back off into deep space. So this is what you would have for a periodic comet, something that's coming back. This would be for the one and done type of comet, the parabolic orbit. So we have those features. The only other things that we need to add to our diagram now, and we really don't have a lot of room, I've tried to compact it here just for the sake of the video, but remember that past Neptune, we have what's known as the Kuiper Belt. And we're saying with KBOs, Kuiper Belt objects. The Kuiper Belt is beyond Neptune. This is the place that we find we find Pluto, Makemake, Haumea, quite a few other dwarf planets out there. These are all Kuiper Belt objects. The reason we mention the Kuiper Belt here is not only is it in our solar system, but it's one of the two birthing grounds of comets. It's believed that the short period comets are derived from the Kuiper Belt, that some of the long period comets actually were kind of born out here in what's known as the Oort cloud. This is still theoretical, but the Oort cloud is considered a nursery for the comets. Again, for these very long period comets are probably derived from this area, this disk of material that's out beyond the heliosphere, out beyond the influence of our sun. And there's rocky and icy material out there. And it seems that, again, long period comets might be derived from that area. So we have two birthing grounds, potential birthing grounds for comets. The Kuiper Belt, again, with KBOs, Kuiper Belt objects. The Oort cloud out here, the theoretical birthing ground for the long period comets. One thing to remember is that distances within our solar system, either within or near our solar system, are measured in terms of astronomical units. Remember that one astronomical unit is 93 million miles, which is approximately the distance from Sun to Earth. It may seem arbitrary, but it's a handy thing. We're the only intelligent life in the solar system as far as we know, and so we do things relative to where we are on Earth. And so one astronomical unit is the Sun-Earth distance, 93 million miles. That's used to measure things in or near our solar system. If we're dealing with interstellar distances, if we're talking about distances to distant stars, then we use light years. And remember, a light year is the distance that light can travel in 1 year. That's something like almost 5.9 trillion miles. So there's a reason, just think about the number of zeros there. There's a reason that we might want some sort of shorthand unit for measuring interstellar distances. The closest star, apart from our sun, closest star to us in our solar system is Alpha Centauri, and it's 4.2 or 4.3 light years away. We're talking about something like 23 trillion miles. So for that reason, we use light years, and it's much easier to say 4.2 or 4.3 light years than to say 23 trillion miles. So it's good to keep in mind that we have these two different ways of measuring distances. All of them are sort of a shorthand version, right? So that we're not having to deal with millions or billions or trillions of miles. or even greater distances than that. So this is the solar system diagram. The way that I've drawn it here is it's really super compact and maybe a little bit hard to see everything, but if you were following along as I did this, you would be able to piece together all the various parts from the elliptical orbit to the parabolic orbit to things having to do with albedo and the things that affect the brightness of planets, the classification of planets as inferior or superior, terrestrial or rocky versus Jovian or gas giants. We see the structure of a comet here. We see the birthing grounds of comets here, and we're reminded of the tail of comets are always pointing away from the sun because of the solar wind and solar radiation that cause the breakdown of the coma and the tail. But again, out in deep space, we wouldn't even see the tail, and that's the most obvious feature of comets anyway, is the big tail. And so that's only going to be shown when the comet is in proximity to our star, the sun. So I hopefully you find this helpful. Thank you for your attention. I appreciate you and the effort you're putting in class. Bye-bye for now.